Hi, this is going to be explaining limits day 2. I think out of all the days of limits notes, this is the day that is the most involved, and it's the most important that you stop the video maybe after every single example, maybe go back and listen to the example again. For your online limits test that you're going to take on Friday, count on having questions like most of these. It'll be another multiple choice test. You're going to have 1 hour to do it, but this is the day, and tomorrow's notes with limits to infinity will be the 2 days that I focus the most on for that test. So just a quick review. Remember that a limit is a location and it's a y value, and in order for a limit to exist, as you're looking at an x value from both the left and the right on the graph, your function or your y value has to come to the same location. Now, it doesn't mean that there's necessarily a y value there. There can be a hole in the graph, a point discontinuity, and there could still be a limit, which is going to come up with a couple of these. Okay, so what you need to do is think about what each of these graphs look like. So my suggestion to you is, as you're looking at every question, maybe graph the function and then kind of pay attention to what I'm saying about the limits, and I think that'll be very helpful. Again, this would be a good day to stop the videos a lot as you're watching it. Okay, so the first example is the limit as x is approaching -2 of the function of 5, which means y equals 5. So if you think about what the graph of y equals 5 looks like, y equals 5 is a horizontal line. It's a continuous function. There's no breaks in it at all. So as you're approaching -2 from both the left and the right, the function value or the y value from the left and the right are coming to the same point. It's coming to a y value of 5. Now, probably the most important thing that you should write down about what I just did is this function, y equals 5, is a constant function, and the limit of a constant is the constant. So that's a real important thing to remember. Now, all of these notes that are on the front of this, if we were in class, I would be kind of going through them one by one by one, but look at the first set of notes, and it says that if you have a constant function, that the limit of your constant is equal to that function. So that's really important, and there will absolutely be one of these questions on your test on Friday. Okay, the second question, if you take a look at the function, we're thinking about the function y equals x plus 3, which is a linear function. It's a continuous function. There's no breaks in it. It would be a line that would have a slope of 1 and a y-intercept of +3. So if you are looking for the limit as x is approaching +1 of this line y equals 3 from the left and the right, we're going to use direct substitution. So all we have to do is substitute the 1 in for x. So you have 1 plus 3, which would be 4. Now you could absolutely verify this by graphing this function and looking for the y value as x is approaching 1 from the left and the right. So you could go to your table, look at your x values. Your y value is coming to a y value of 4. So when you have a continuous function that doesn't have any breaks in it at all, you can go to direct substitution for limits. Now, the next function, y equals 5 times 3x squared plus 2, that's a parabola. A parabola is a continuous function. There's no breaks in it at all. So as you're approaching an x value of -1 from the left and the right, if you look at this graph is coming to the same y location. Because there's no breaks, we can go directly to direct substitution. Because we're going to direct substitution, this is simplified. We're going to substitute x with -1, drop out the limit notation. So it'll be 5 times 3 times -1 squared plus 2. -1 squared is +1 times 3 is 3 plus 2. You get 5 in the parentheses, and we multiply those together. The y value from the left and the right as this function is approaching -1 is 25. Now, this next example, x over x plus 2, that wouldn't be a continuous function. something is going on at an x value of 2. It might be a point discontinuity, it might be a hole in the graph, it might be a vertical asymptote, an infinite discontinuity, but it only occurs when x is 2. So I know that x cannot equal 2, but I want the limit as x is approaching 4. So if you graph this function and you look as x is approaching 4 from the left and the right, what is the y value that this function is approaching? It's going to approach, we're going to go to direct substitution because the 4 doesn't make this function undefined. So it'll be 4 divided by 4 plus 2, so 4 over 6, so 2/3. And again, you can verify that by looking at your graph. Okay, now those first 4 were pretty straightforward, and now it's going to get a little bit more involved, and I'm going to slow down with the explanations on these. So the next example is the limit as x is approaching 9 of the function of the square root of 4x minus 11. Okay, so what you should do is you should graph this function and see if it even exists at an x value of 9. When you take a look at the graph of this function, the graph looks like this. So it's undefined, or the domain of the function starts a little bit more than 2, at an x value of a little bit more than 2 to positive infinity. At an x value of positive 9, there is definitely a y value for this function. Because I verified it using my graph and I know that it comes to the same y location from the left and the right as x is approaching 9, I can go to direct substitution. As soon as you go to direct substitution, you drop out the limit notation. So it'll be 4 times 9 minus 11, 36 minus 11, the square root of 25. So the limit of this function, remember, a limit is a y value. As x is approaching 9 from the left and the right on this graph, the function itself from the left and the right is coming to the same y location, which is 5. Your limit is your y value. Now, with example number 6, it's the limit as x is approaching positive 2. So from the left and the right, as x is approaching positive 2, when you look at this function, does it come to the same y location? And this function is y is equal to x squared plus x minus 6 divided by x minus 2. Okay, well, I know immediately from looking at this function that x cannot equal positive 2. So if I asked you what is the function value at 2, you would say undefined. There is no y value at an x value of 2. That doesn't mean the function is not coming to the same y location from both the left and the right. So this would be a really, really good time to pick up your calculators, put this function into your calculator, take a look at the graph. So here's what my graph looks like. It certainly looks like a continuous function. It looks like a line. So as I approach an x value of positive 2, an x value of positive 2, from the left and the right, my function certainly looks like it's coming to the same y location. But if I look at my table of values, at an x value of positive 2, there's no y value. So if I ask you the function value of 2, if I ask you f of 2, meaning when x is 2, what is your y value? You would have to say that it's undefined. But that doesn't mean it doesn't have a limit. Again, if you look at the graph again, from the left and the right, as x is approaching positive 2, it's definitely coming to the same y location. So what we're going to do is we're going to simplify the function, and then after we're done simplifying, we're going to go to direct substitution, and that will be our limit. So keep your limit notation in until you're done simplifying as x is approaching positive 2. The numerator will factor to x plus 3, x minus 2, divided by x minus 2. Now I know that x cannot equal 2, but that doesn't mean that it's not coming to the same y location. These are going to cancel. So I'm left with the limit as x is approaching 2 of x plus 3. I still have to keep in mind that x cannot equal 2. The function is definitely undefined at an x value of 2. But now that I'm done simplifying my function, I can go to direct substitution. When you go to direct substitution, I forgot the 2 there. When you go to direct substitution, you drop out your limit notation. So it's going to be just 2 plus 2, 3. Direct substitution, I'm substituting 2 in for x plus 3. So the limit would be a y value of 5. Now let's see if that makes any sense at all. When you look at your table of values here, as x is approaching 2 from the left, it's coming to a y value of 4. As x is approaching 2 from the right, it's coming to a y value of 6. Even though the function is undefined at an x value of 2, from the left and the right, it's coming to the same y location, which is y location of 5. So the limit is 5. So the limit as x approaching 2 is 5. F of 2, the function value, is undefined because there's no y value at that exact point. Okay, now, example number 7. I promise there's one of these on your test on Friday. So this is one that you really want, this example and example number 9, you really want to pay a lot of attention to. So for example number 7, we're trying to find the limit as x is approaching positive 4 of the square root of x minus 2 divided by x minus 4. Well, immediately I know that x cannot equal 4. Definitely it can't be 4 because that would give us a 0 in the denominator. So if I ask you, what is the function value at 4? What is the y value when x is equal to 4? It's undefined. That doesn't mean that there's not a limit, that it doesn't approach the same y value from the left and from the right. So again, this is a really good time for you guys to pick up your calculators, take a look at the graph. Now when I use a standard window, it kind of looks like a line right along the x-axis, so that's not a very good window. But I'm going to change the window so I can look at this graph better. I'm going to use a window of -2 to +10, and I'll use a scale of 2s. And from -1 to +1, and I'll use a scale of 1 is fine. And now when you look at the graph, you can see there's a hole right there in that graph where x is 4. So, and if you take a look at your table of values, where x is 4, there's an error message. So definitely the function is undefined at an x value of 4. Okay, but again, looking at the graph, as x is approaching 4 from the left and the right, you can see it's coming to the same y value. It's converging in the same y value. So now we have to simplify this function. When we're done simplifying it, we'll go to direct substitution, and that'll give us our limit. Now, to simplify the function, you're going to use the conjugate of the numerator. When we were simplifying square root radical binomials, and we used the conjugate of the denominator to give us a rational denominator, a rational number in the denominator, that's similar to what we're going to do here. But here we're going to use the conjugate of the numerator to simplify the function. So the conjugate of the numerator is the square root of x plus 2. And I'm going to multiply this whole function by 1 using the conjugate of the numerator. So the square root of x plus 2 over the square root of x plus 2 is equal to 1. I'm multiplying the function by 1, so I'm not changing the value of the original function. But this is going to help us find where that function converges from the left and the right as x is approaching 4. So the limit as x approaches 4, I'm not going to drop that out until I'm done simplifying the whole function. When you multiply conjugates, you only have to multiply first and last. The outside and the inside will drop out with FOIL. So first times first, the square root of x times the square root of x is x. Last times last, a -2 times a +2 is x minus 4. So that's the numerator multiplied. The denominator is x minus 4 over the square root of x plus 2. I didn't multiply the denominator because these cancel. So now I'm going to evaluate the limit as x is approaching +4 of 1 over the square root of x plus 2. So I am done simplifying the function. I can't simplify it anymore. This is the point where I'm going to go to direct substitution. You drop out the limit notation, you replace x with 4. So 1 over the square root of 4 plus 2. So it's 1 over 2 plus 2. So the limit as x is approaching +4 of this function is 1/4. I'm going to go to my table of values again and see if that answer even makes any sense. Here's my table of values. 1/4 is 0.25, and from the left, it's coming to 0.267, from the right, 0.236, so that limit of 1/4 or 0.25 makes sense. So just for clarification purposes, this is the limit of the function. As that function is approaching 4 from the left and the right, it's converging on a y value of +4. But if I were to ask you f of 4 of this function, the square root of x minus 2 over x minus 4, f of 4 would be undefined. Now, when a function value doesn't exist, it's undefined. If a limit doesn't exist, then its DNE does not exist. Okay, example number 8. Example number 8, we're looking for the limit as x is approaching +1 of the function x plus 1 over x squared minus 1. Now, I know that this function, x cannot equal plus or minus 1. That would give me a 0 in the denominator. Remember that denominator is the dots factoring. So there would be two values that would make this function undefined. I don't know if, as x is approaching 1 from the left and the right, if this function is approaching the same y value. I'm going to show you the graph after I do the algebraic part of it. So if we try to evaluate the limit as x is approaching +1, I'm going to simplify the denominator. So it'll factor to be x plus 1, x minus 1. These cancel. I'm trying to find the limit as x is approaching +1 of 1 over x minus 1. I'm done simplifying the function. If I go to direct substitution right now, drop out the limit notation, it will be 1 over 1 minus 1, 1 over 0. That's undefined. So I knew that the function was undefined there, but when I evaluated the limit, I didn't come to an integer value or a y value. So let's take a look at this graph. I'm going to do a standard window, and that's what the graph looks like. So what is going on at an x value? This is a TI-83 calculator, and remember that the TI-83 puts in your vertical asymptotes. There's a vertical asymptote at x equals +1. The function is definitely undefined at +1, but look at as x is approaching 1 from the left. As x is approaching 1 from the left, your function is going to a y value of -infinity. As x is approaching 1 from the right, your y value is going to +infinity. It's not approaching the same y value, so the limit does not exist. So you would say the limit as x approaches 1 is DNE does not exist, but f of +1 is undefined. Using the graphs is very, very helpful with limits. Okay, Then example number 9 is very much like example number 7, and there will definitely be one of these on your test on Friday. Okay, example number 9, we're going to evaluate the limit as x is approaching 25 of the square root of x minus 5 divided by x minus 25. All right, I know right away x cannot equal 25. So if I ask you what is the function value at 25, you would say it's undefined. That doesn't mean that there's not a limit. So we're going to simplify this function. You should really look at the graph of it too, and look at as x is approaching 25 from the left and the right, does it look like it's coming to the same y value? And it does. So even though the function is undefined, this is another situation where there's absolutely a limit. So I'm going to simplify this a lot like I did number 7. The limit is x is approaching 25 of the square root of x minus 5 over x minus 25. I'm going to use the conjugate of the numerator again. So the conjugate of the numerator is the square root of x plus 5. I'm going to multiply by 1. So I wrote 1 as the square root of x plus 5 over the square root of x plus 5. Multiplying by 1 doesn't change the value of the original function. In the numerator, when you multiply conjugates, you only have to multiply first and last. Square root of x times the square root of x is x. Negative 5 times positive 5 is a negative 25. I'm not going to multiply the denominator yet. X minus 25 divided by the square root of x plus 5. And I didn't want to multiply the denominators yet because I wanted to see if the numerator would cancel, and it does. So when I cancel this out, I'm left with the limit as x is approaching 25 of 1 over the square root of x plus 5. So now I'm done simplifying the function. Once you've simplified the function as much as you can, you drop out the limit notation, you go to direct substitution, you replace x with 25. So it's 1 over the square root of 25 plus 5. This is 5 plus 5. So the limit as x is approaching 25 from the left and the right comes to the same y location, which is 1/10. This is another situation. Well, although the function is undefined, the limit still exists. Now, the last example, example number 10, we're looking for the limit as x is approaching 0. So if you were to graph this function, and you look at this function as x is approaching 0 from the left and the right, is this function coming to the same y location? If it is, then that's what the limit is. So this function is 1 over x plus 8 minus 1 over 8 divided by x. Okay, well, it's clear that x cannot be equal to 0. I give you a 0 in the denominator. The function is undefined at x equals 0. So I know x cannot equal 0. That doesn't mean that when you look at the graph from the left and the right, as x is approaching 0, that it doesn't come to the same y location. And as a matter of fact, it does. So what we have to do is we're going to simplify this complex fraction. Remember that this is an x over 1. And when you simplify a complex fraction, you multiply everything in the fraction by the LCD. And the LCD of this complex fraction is going to include all the denominators. So I have to include x plus 8. I have to include the denominator of 8. And I have a denominator of 1. I don't have to include the 1 because 1 times anything is itself. So to simplify this, I'm going to multiply every piece of the complex fraction by the LCD, which is 8 times x plus 8. So 1 over x plus 8 I'm going to multiply it by the LCD, which is x plus 8 times 8 minus 1 over 8. I'm going to multiply that by the LCD, x plus 8 times 8, divided by, the denominator is x times the LCD, x plus 8 times 8. Okay, so all I've done right now is I'm showing that I'm multiplying every piece of it by the LCD. Keep the limit notation in until you're done simplifying, and in the very last step you'll go to direct substitution. So these x plus 8's cancel, and here you're left with just an 8 minus these 8's cancel, and you're left here with x plus 8. And in the denominator, I'm not going to distribute yet. I'm going to leave it as 8 times x plus 8. Right? We're going to evaluate the limit as x is approaching 0. Distribute this negative. So you're going to be left with 8 minus x minus 8 over 8x times x plus 8. When you combine like terms in the numerator, limit as x is approaching 0 of, the 8's cancel, so you have negative x over 8x times x plus 8. These x's are going to cancel, so you will have, I'm going to have to come up to here, the limit as x is approaching 0 of negative 1 over 8 times x plus 8. Done simplifying, go to direct substitution, drop out the limit notation, replace x with 0, negative 1 over 8 times 0 plus 8. Negative 1 over 8 times 8 is negative 1 over 64. So here's another situation where the function is undefined at x equals 0, but the limit of negative 1 over 64 exists. So when you're looking at this function, at the graph of the function, as x is approaching 0 from the left and the right, it should be very clear that it's coming to the same y location. Again, this is probably the most important day of notes for your test on Friday, along with tomorrow's notes on limits to infinity. I hope that you guys are all doing well, and I look forward to seeing you all soon.